Hello, welcome to chemistry class. Today's learning objective is about bonding in metals. So, coming to the bonding in metals, first let us see arrangement of atoms in the metals. Metals are found to crystallize either in body center cubic structure BCC or face center structure or FCC or hexagonal closed packed HCP structure. You can rationalize this observation on the basis of the arrangement of atoms in the metals and that yield a close packed structure. So, assuming atoms to be hard spheres, it can be easily deduced that packing efficiency, volume occupied by total volume, BCC, FCC, HCP, almost they equal to 68%, 78%, 74%, respectively, and compare thus 52% it is about for the simple cubic arrangement. So it can be suggested that simple packing efficiency is higher in BCC. The packing efficiency you can see in BCC, FCC than to the simple cubic structure. So metals prefer to crystallize in one of these structures. The structures are normally described in terms of smallest repeating unit called as a unit cell. So the entire space lattice can be generated by translation motion and or a unit cell along the three axes, that is xyz coordinates, and unit cell is so chosen that it has the same symmetry as that of the lattice. Now there are different theories of bonding in metals. So any theory of bonding in metal must account their characteristics. Whatever theory you any theory of the bonding in the metals, they should account for their characteristic properties like high luster. They should explain that theory should explain luster, complete opacity, thermal conductivity, electrical conductivity, and different laws, the electrical conductivity, and the variation of the resistivity to the magnetic field. So all this should be accounted for the theories. So in that theories, now for the bonding in metals, there are three different theories. You are having the free electron theory, valence bond theory, and molecular orbital theory. So today's class, I'm going to explain you about the free electron theory. See, just have a look onto the periodic table. Yeah, all the red ones are the metals, and the yellow ones are metalloids. Blue ones are non-metals. So this is a description of the metal, non-metals, and metalloids. Now, metals in the periodic table. Currently, the scientists have discovered 118. They have discovered 118 different elements about different elements in the periodic table. In that, 91 of the 118 elements in the periodic table are the metals. 118 are about the are of metals, and 17 are non-metals in the periodic table. So the gases hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. And one is the liquid, that is a bromine, and few are the solids. So carbon, phosphorus, sulfur, selenium, and iodine. These are all the solids. So there are 17 nonmetals, out of which some of them are the gases, some of them are the liquids, and few are the solids. And in the metalloids, coming to the metalloids, you are having boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatin, all these all these are the elements found step like line between the metals and non-metals. Characteristics of the metals. So metals have peculiar shining. Yeah, of course, they have shining on the surface, that is metallic luster, and they have high density, and they are the hard substances. So metals have high melting point and boiling points. Metals are the good conductors of heat. Metals have high electric conductivity, which decreases with temperature. These have high elasticity. These are the characters. So in the periodic table, you have seen 18 elements metals and 17 non-metals, remaining are the metalloids. So out of these, the general characteristics for the metals are, see, they have shining and they have metallic luster, they have high density, they are hard substances, they have high melting point and boiling points, the good conductors of heat, they have high electrical conductivity which decreases with temperature. And still, the metals are malleable, ductile. They can be hammered into sheets and can be drawn into thin wires. They're opaque to light, and they form metals form solid solutions called alloys. So daily we are using these alloys in, with each other and very easily. Metals form solid solutions called alloys on combination with each other very easily. Metals are generally electropositive elements. Finer the metal particles, more reactive is the metal. Finer are the particles, more is the reactivity. Now, let us see the bonding in metals, and metals believed to possess special type of bond known as metallic bond. They are believed to possess the special type of bond that is metallic bond. Nature of the metallic bond can be explained in terms of theories. One is free electron theory, the second one is the valence bond theory, and the third one is the molecular orbital theory. Now let us have a look onto the free electron theory. Free electron theory, this theory was proposed by Drude and Lawrence in 1900, and this what he explains is high electrical conductivity, thermal conductivity of the metals. Some of the metals lose one electron, some of the atoms they lose one or more ions, but they are free to move throughout the metal. See, let me give you a clear explanation. Free electron theory, it was proposed by Drude and Lawrence in 1900, and it was proposed that the metals consist of the positive ion cores with valence electrons, and these valence electrons are moving freely among the cores. So the potential energy, the potential field of these cores is assumed to be constant throughout the metal, and the inter electron repulsions are neglected. The behavior of these free electrons moving inside the metal is considered as non-interacting and similar to that of molecules in that of ideal gas. So despite of the charge associated with electrons. So this theory refers to as a free electron gas model. And successfully you can explain, for example, you take electrical conductivity of the metal, it can be explained on the basis of availability of free electrons. And similarly, metals are opaque. It is explained on the basis of absorption of light by free electrons. So due to these free electrons, These are absorbing the light and they are opaque. When a light beam falls on the surface of the metal, free electrons are set in forced oscillations having some frequency as that of incident light. So, since incident light is thus absorbed by the metal, it appears to be opaque even for the light. So, it is opaque for the light, and similarly, these conduct the electricity due to the free electrons. So, here the model is referred as free electron gas model. So, all the instant light gets absorbed and opaque nature comes. And one more success of the electron gas model is the ability to explain the Ohm's law. This theory was able to explain Ohm's law. So in absence of electrical field, the free electrons in a metal move random directions. So there is no electrical field. In absence of electrical field, the free electron in a metal moves in random directions. But an external electrical field, it is applied, the electrons are getting accelerated. So, yeah, after giving this postulates will be explained. And moreover, the acceleration gained by the free electron, it can be given A is equal to E by M. So, where E is the charge of the electron, M is the mass of the electron. So, A is equal to E by M. Okay, so the acceleration of the free electron can be explained. Acceleration is equal to E by M, charge by mass of the electron. Okay. So this theory it explains the high electrical conductivity, thermal conductivity of the metals. Some of the atoms lose one or more ions but are free to move throughout the metal. Some of the atoms lose one or more ions, but they are free to move throughout the metal. So, due to these free electrons, you can explain about the electrical conductivity. And thus, the free moving electrons are said to be delocalized. So, they keep on moving, so they are delocalized. Thus, according to this one, a metal may be regarded essentially of a positive ion or the cations immersed in the sea of mobile electrons or the sea of negative charge cloud. Okay, see here you can see the diagram how this is the electron free electron gas model. Free electron gas model. You can assume a pump. You can assume this watermelon. How the black seeds are there in between. In the similar fashion, here these electrons are also there. See here, this is the metal and the electrons are moving free, and this is the nuclei, yeah, and the electrons are moving. So they are non-directional. So here he explains the characters that the bonds are also non-directional, and the electrons are not shared with one atom in one direction. Each electron is shared by number of atoms and with many neighboring atoms in different directions, in all directions. So the electrons are shared with many neighboring atoms in all directions. See, and when E is the charge of the electron, see A is equal to E by M. So the drift velocity Vd of the electrons is given by Vd is equal to E by M. So E by M and E into Vd is equal to small e by m, capital E into rho, the collision time. Now, you get substituting all the equations. I is equal to R V by R, Ohm's law we get. We get I is equal to V by R, Ohm's law. So, basing on the Drude's electron gas model, Lawrence in 1907 applied kinetic theory of gases, Maxwell-Boltzmann statistics, and to assembly the free electrons. And since this is a based on classical ideas of the Maxwell, the Boltzmann statistics and the Drude Lorentz theory is called as the classical free electron theory. See later on, So previously 19th century, 1900, this model was given. But in 1907, the electron gas model, Lawrence in 1907, he has applied kinetic theory of gases and Maxwell-Boltzmann statistics to free electrons. So, and basing on these classical ideas of the Maxwell-Boltzmann statistics, Drude-Lawrence theory is called classical free electron theory and one of the earliest success of the Drude-Lawrence theory. So similar, the semi-quantitative agreement has been done here. It states that the ratio of the thermal conductivity K and to the electrical conductivity sigma of the metal is constant at temperature. K by sigma is equal to C into T. K by sigma is equal to C into T. Here it's not given, but I'm just giving you a more broad explanation, just explaining you in a very broad manner, but that's not required in order. So here, what the formula was given is, the formula is K by sigma is equal to Ct, capital C, capital T. C is the constant, T is the temperature, and K is the thermal conductivity, sigma is the electrical conductivity. Thermal conductivity by electrical conductivity of a metal is equal to Ct. C is constant, T is temperature. So Drude-Lawrence theory attempted to derive an expression for C by applying kinetic theory for the random motion of these electrons. Okay, so anyhow, the characters what were explained about the bonding are, there are non-directional bonding. The bonds are non-directional and the electrons are not shared with one atom in direction, but they are shared with many other neighboring atoms in all directions. Now, which type of the bond is that? Which type of bond is that? Valence electrons are attracted simultaneously by large number of atoms. So net binding energy is very small and bond formed is very weak. So it's a weak bond. Valence electrons, they're getting attracted simultaneously by large number of atoms. So the net binding energy is very, very less and the bond formed is therefore very weak. Okay. So binding energy is less, therefore the bonding is weak. Now coming to the thermal conductivity. So the characteristics, whenever any model is given, they have to be explained. They should be able to explain thermal conductivity, electrical conductivity, the bonding nature. All this should be able to explain. So the theories should be able to explain about the characteristics of the this metal. So any of the theory must account their characteristics: high luster, opacity, thermal conductivity, electrical conductivity, applicable of the Ohm's law we have applied, and it should be applicable of the Wiedemann-Franz law we have applied even that, and the ratio of the thermal conductivity to electrical conductivity should be constant. Even that should be given. Just now I gave you K by sigma is equal to Ct, and variation of the resistivity in presence of external magnetic field. Okay, and several theories in that this theory is the best. This theory could explain the, could satisfy the characteristics, the what characteristics could satisfy some of the properties of the metals. Now the coming to the thermal conductivity. when part of the metal is heated When a part of the metal is heated, electrons in that part absorb energy from the source of heat. So just you take a metal and you heat it. So the electrons in that part, they absorb energy from the source of that heat. And these energetic electrons move to the cooler part. Whatever electrons are getting energy, they move to the cooler parts and they transfer kinetic energy to the electrons present in the part on collision with them. And that process goes on till the temperature of all parts of the metals become same. So when a part of the metal is heated, the electrons in that part gets absorbed and the energy of the source of heat. These energetic electrons move to the cooler parts. They transfer the kinetic energy to the electrons present in the part on the collisions with them. And the process goes on till the temperature of all parts of the metal becomes same. Yeah, this process continues till it's getting the same. All parts get the same temperature. So that is thermal conductivity. A part of the metal is heated, electrons in that part absorb energy from the source of heat, and the energetic electrons move to the cooler parts. Yeah, that's what you heat anything on the you heat any vessel or a container. What happens? Here they get the part whichever is getting heated. They get there the electrons. They're getting energy. They move to the cooler parts. They transfer the kinetic energy to the electrons present in the part on collision with them. So these electrons move and they collide. After colliding, they transfer that energy. Energized electrons transfer the energy to that part where it is cool. And the process goes on till temperature, a complete container gets the same temperature. The process goes on till the temperature of all parts of the metal becomes same. So, as I've told you, a best example you take a metal, anything alloy one, you take and you put it on the stove and you heat it. Just one part you are heating, but the heat is getting transferred totally to that container. How? That part gets heated and they're getting energized electrons. These move to the cooler parts and they get collided there, and the cooler part on collisions gain energy, and that energy when they are getting heated up. In this way, the temperature is completely transferred to the whole container, and thereby the it becomes the same temperature. The whole metal comes onto the same temperature. So this is thermal conductivity. Now, what about the electrical conductivity? So once if you talk about the electrical conductivity, as I've told you, the next characteristic which should be satisfied for this theory is electrical conductivity of the metals. What is conductivity? What is conductivity? Passage. Yeah. What is the conductivity? Yeah, now I'm going to explain you the metals are the good conductors of the electricity due to presence of mobile electrons in the metals. So, when you take for example silver, you have sigma value and K value, electrical conductivity value and K value. Similarly, for copper, aluminum, sodium, cadmium, iron, for all these, you can see the sigma values and K values, thermal conductivity as well as electrical conductivity. So, the you can explain that these metals are the good conductors, good thermal conductors and electrical conductors. It supports the root theories. Okay, and this how are these electrical conduct good conductors of the electricity? Metals are the good conductors of electricity due to the presence of mobile electrons in metals. When potential difference is applied across the metal sheet, free electrons start moving towards the anode. Metals are the good conductors of electricity, and due to presence of these mobile electrons in the metals, due to presence of these mobile electrons, when there is any potential difference, you see electrochemistry, zinc rod dipped in zinc sulfate, copper dipped in copper sulfate, zinc is connected to the potential difference, and even the copper, the electrodes are getting connected. Those are the metal electrodes. Why we are able to connect just due to the electrical conductivity. So when a potential difference is applied across the metal sheet, free electrons start moving towards the anode, and new electrons are discharged from the negative electrode, and electrode leading to the continuous flow of the electrons. So current starts flowing from negative to positive. See in an electrochemical cell, I've told you, no? Yeah, you can take that one as an example for the electrical conductivity. Metals are good electrical conductivity can be explained taking that example. So metals are good conductors due to passage of the mobile electrons. So when a potential difference is applied across metal sheet, free electrons keep on moving. Free electrons start moving towards the anode. And similarly, from anode to cathode, they keep moving. Why it arises? It is due to the free electrons. And new free electrons are discharged from the negative electrode, and this leads to the continuous flow of electrons. So current starts flow from negative to positive. This is a good illustration for the electrical conductivity of the metals by free electron theory. And you can see the diagram clearly explains you. Have a look onto this. These are the nucleus and these are the electrons, free electrons. Here are the free electrons. Then moving this. Direction of the electrons. The electrons are moving, electrons are moving, electrons are moving. And these two are the electrodes. This electrode is connected to one potential here, and this electrode is connected to the another terminal, anode and cathode. You can take here, this is the anode and this is the cathode. This anode and cathode are connected, and these from these electrodes, the electrons are coming out and moving into the solution. And after this is coming into the electrolyte, they move on to the next electrode. So it is due to the free electrons. So these free electrons keep on moving, and there is a potential difference and there is a conductivity of the electrons. Yeah, this is a clear evidence for the electrical conductivity in the metal crystals. Yeah, metals are the good conductors of the electricity due to presence of that mobile electrons in the metals. So metals are the good conductors of electricity due to presence of those mobile electrons in the metals. When a potential difference is applied across metal sheet, free electrons start moving towards anode, and new electrodes are discharged from the negative electrode. So whatever it may be negative or the positive electrode, the electrons keep moving from one electrode to other electrode through this electrolyte, and there is continuous flow of electrons. And you can see the potential difference applied and the current starts flowing from negative to positive. Therefore, you can clearly this is a good example for the electrical conductivity in the metals. Now, coming to the alkali metals, the another character which can be explained is alkali metals are soft and have low melting points. One valence electron for each atom to enter the delocalization. So, alkali metals soft and have low MP. Alkali metals have only one alkali, the first group elements. They have only one valence electron for each atom to enter the delocalization. Therefore, it's a weak bond. So, soft and have low melting points. They get easily melted up. Coming to the transition elements, they have strong bond and have high melting point. Transition elements have strong bond and they have high melting point due to the presence of the more valence electrons. Transition elements have more valence electrons, high melting points. Alkali metals, alkali metals, only one valence electron and low melting point. These are soft. Okay. And the reason for this one, and there's a high MP and low MP. Why? You can explain due to presence of more valence electrons. The bond is strong with high MP. The bond is strong, they have high melting point. Why the bond is strong? Due to presence of more valence electrons. Here the bond is soft, low melting point. What is the reason? Due to only one valence electron and a weak bond. This is a strong bond. And the other characters which can be explained for the free electron theory are ductile and malleability. It is due to them what is ductility and the malleability. You can draw them into thin wires and sheets. That is the ductility and malleability. We have seen the free electron model due to the non-directional nature of the metallic bond. There you could see any bonding. So due to non-directional nature of the metallic bond, they can be easily drawn into the wires and thin sheets. And due to this fact, on application of force on the metals, they can easily move from one lattice to another lattice, and thereby the shape of the metal gets changed. So, ductility and malleability is very clear for this theory. Because of non directional metallic bond, the application, once a force is applied, the ions move from one lattice to another lattice. Therefore, the shape is getting changed. So, they can be drawn into wires and sheets. I hope you have understood this theory. But before ending the class, what are the defects of this theory? So, what are the defects of the free electron theory? So, the most noticeable failure of the Drude-Lorentz model is it is inability to explain the discrepancy between observed and the predicted values of specific heat. Specific heat couldn't be explained properly, and however, it has the inability to explain the discrepancy between observed magnetic properties. So, proper magnetic property is not properly explained. Specific heat couldn't be explained properly, and the electron has a magnetic moment with its spin classically, and it should that is not being explained clearly. And it has a inability. This theory has inability to account for the positive carriers in metals. Conduction by free electrons is able to do, and this will give negatively charged carriers only. But some cases, zinc and cadmium, if you take, they are positive carriers. Even he is able to explain only basing on the electrons. Why not put the positive carriers? He is not able to give the clear explanation for specific heat of the metal, and he is not able to give the clear explanation about the magnetic properties. So, specific heat of the compounds is not explained. At the same time, this magnetic properties are also not explained, and he is explaining the electrical conductivity, magnetic prop. He is sorry, he is able to explain clearly about the melting points and malleable ductile properties, electrical conductivity, and thermal conductivity, just basing on the electron nature. But he is not able to give about the positive carriers. He is giving only about the negative carriers. So I hope everybody, this is the theory, free electron theory, given by Drude and Lawrence. Okay, so today's class, what I have discussed is about the bonding in metals. So in the bonding, before that, the crystals we have seen, phase center, HCP, PCC, simple cubic structures. So, and basing on that, how the metal crystals are there, and we have to know which type of bond is there. In order to explain about the bond, there are three theories: free electron theory, and valence bond theory, molecular orbital theory, or band theory. Okay, so the free electron theory. Now, how the periodic table is there? What are the metals, non-metals, and metalloids? And how many metals are there? What are the characteristics of a metals? And according to free electron theory, the how what is the bonding? Non-directional bonding. Just like a this watermelon model it is there, and the bond is weak. Thermal conductivity, electrical conductivity, melting points, malleability, ductility are explained. But magnetism, specific heat is not explained. And with respect to positive carriers, the conductivity is not explained. And remaining properties are not explained. Okay? So this is for today's class. Thank you everybody.